In this video we'll be looking at a feature of Simio called rate tables, where we can specify arrival rates that vary with time. And so the model that we'll be using is a hot dog stand, a lunchtime hot dog stand where customers arrive, and if there's a queue, they wait in the queue, and then they're served by one of the workers at the hot dog stand. So a very typical street vendor that you would see. The hot dog stand is open from 9 a.m. to 3 p.m. daily, and historical records show that there are approximately 210 customers per day, and that the time to fill any customer's order is approximately 1.5 minutes, but is highly variable due to ordering, paying, and that type of thing. The interesting part of this model that we haven't seen before is that the customer arrival rates vary with time. And so you can see in the image here, and sorry about my hand drawing of the arrival rate function, but when the hot dog stand opens at 9, you can see that the customer arrival rate slowly ramps up, and then around lunchtime starts to quickly ramp up, and you have the lunch rush, and then the arrival rate declines over the day. So what I'm plotting here is the customer hourly arrival rate versus time of day. And what we will do in our model is we will approximate this continuous function by using these hourly rates. And so what we see here is that we have between the hours of 9 and 11 an arrival rate of 20 customers per hour, between 11 and 1 60 customers per hour, and between 1 and 3 25 customers per hour. And so if you add that up, we have 20 and 20, 60 and 60, 25 and 25, and that is our 210 customers per day that we see. So let's get started with our model. So we have initially a very simple single server queuing system here. So let's put down our standard source server sync, and we'll use paths so that we can actually see the customers moving through the system. And then I'll grab my model entity and rename my entity instance as customers. And then we can rename the server to vendor. And so we have our queuing system where if we run just with the default, we have customers that arrive, they go and they wait in line, the vendor serves them, and then they depart. So initially, let's look at this system as a standard M1 queuing system. We'll assume that the external arrivals are Poisson, so the inter-arrival times are exponential, which seems to be a fairly reasonable assumption for customer service systems. We'll also assume that the processing times are also exponential because the statement that the times are highly variable. So we have the mean service time of 1.5. We have customers per day of 210. And so if the hot dog stand is open from 9 in the morning to 3 in the afternoon, that's 6 hours per day. And so our customers per hour will be 35. And this is our arrival rate over the entire day. And our service rate, if each person, let's just start out assuming that we have one worker, can process in 1.5 minutes, we get 60 divided by 1.5 minutes, so we have a service rate of 40. And so our utilization of our system is simply going to be 35 divided by 40, or 0.875. And so we would expect that, at least from our MM1 queuing perspective, that our server will be able to keep up. And so the only other parameter we need right now is our inter-arrival time. So if we just take 60 divided by our 35, we see that our inter-arrival time in terms of minutes is 1.714286. So we can put those values in our Simio model. So let me see if I can have both of these things on the screen. I can for a little bit anyway. And so 1.714286. So this is exponential with a mean of 1.714286 minutes. Let's see here. Did I get that right? 1.714. 1.714286. 1.714286. And then the processing times are also exponential with a mean of 1.5. And so that is our standard MM1 queuing system. And so we can run the model and take a look at the results, some sample results. And so let's just run, again, let's just say that we're going to run for 100 hours. And so we'll fast forward now, and we get to our 100-hour point here, and then we can go look at our standard results. And what we're interested in is looking at that the utilization of the server, which we expect to be, that we calculated, it should be around 8.875, and in fact from our single replication or a single interactive run, we see that's 87.4. So at this point we're looking at our model and we're satisfied that we've implemented the standard MM1 queuing model with the given parameters. Of course, our system is not a standard MM1 queuing model because we have this time varying arrival rate. So the first thing I'm going to do is I'm going to set the model to run for an unspecified time length, and then I'm going to turn the arrivals off at 6 hours. And so this would say that we will have arrivals that occur until 6 hours into the replication, and the model will actually run until the last customer leaves. So this will implement a system where the hot dog stand actually stops taking arrivals at 3 p.m. but continues to serve everybody who's in the queue. So I'm going to go in the start time actually and set this to 9 a.m. so we can actually look at the time, the actual time. So we have a starting time of 9 a.m. and an unspecified or infinite run length, but we turn the arrivals off at time 6. And so now when we run our model, if we run in fast forward mode, you can see that in this particular run we ran until time 6.12. So when 6 o'clock or when 3 o'clock occurred, the last arrival, the arrivals were shut off. There was still at least one customer in service or in queue, and that final customer left at time 6.12. And so now what we have is a system that runs one effective work day. And so to evaluate this, we need to set up an experiment. So I'm going to set up my experiment to run, and we'll have just at least start out with our default 10 replications. Let me reset the model, and then we'll add a couple of responses. Let's add a response for the utilization of the server. So this will simply going to be our vendor object, capacity, scheduled utilization. So this shows the utilization of our server, and then we can also add the standard queuing results of number in system. And so the number in system will be customers, population, number in system, average, and time in system. So time in system, customers, population, time in system, average. And so now when we run, we can see that we get our utilization, our number in system, and our time in system. And while we're here, let's convert our time in system to minutes. And we have our standard results. Now keep in mind, when we're comparing this to our queuing results were, or our utilization that we computed was a steady state result, and what we have here are for a terminating system that starts at 9 in the morning and runs until 3 o'clock or when the last customer leaves. So we wouldn't necessarily expect those numbers to completely match up. So as one final addition before we incorporate the time varying arrival rate, I'm going to add a status plot so that we can view the number of entities in the system over time. And so we'll put the plot down, and I want the plot to be for, let's make it for 7 hours, because we're again not exactly sure when the system's going to terminate. So actually let's make it 8 hours. So you can see we have from 9 to 5, and the expression that I want to plot is the number in system. So I'm going to do customers, population, number in system. Well, if I could type number in system. And this time I'm not doing the average, because what I'm interested in, at least initially, is the instantaneous numbering system. And so now when I run my model, we can see that we're tracking. Let me speed this up a little bit. Let's go to 10. Even faster. Let's go to 50. We can see that the plot is showing us instantaneous at any point in simulation time how many customers there are in the system. And so our interactive run has run to completion. You can see we have our 6.12 hours, just as we had before. And in our plot of the number in system, we see that the number in system actually goes to 0. And this would be right here at time 6.12. Okay, to implement our time varying arrivals, we will use Simio rate tables. And with a rate table, we essentially specify the intervals and then the hourly arrival rate. So interval and hourly arrival rate. And the way we have our model specified, we have 3 2-hour intervals. So an interval from 9 to 11 with a rate of 20, an interval from 11 to 1 with a rate of 60, and an interval from 1 to 3 with a rate of 25. And so we'll go back to our Simio model and stop the model, go to Data, then there's a Rate Tables option over here on the left, and so we'll just create a new rate table. By default, Simio gives us an interval size of 1 hour and 24 intervals per day. So we're going to change our interval size to 2 hours, and we only need 3 intervals for a total of 6 hours. And so now over in the table, we can see that we have a starting offset and an ending offset. So we start our simulation at time 9, so our offset is 0, and this arrival rate will be in effect for our 2-hour period from 9 to 11. And so this is our 20 customers per hour rate. Then our 60 customers per hour rate between the offset of 2, which would be 11 o'clock to 1 o'clock, and then 25 entities per hour. So when you implement a rate table, you want to be sure that the only way to specify these is in events per hour. So regardless of what your interval size is, so our interval widths are actually 2 hours, but we have to make sure and specify the hourly rate for arrivals. So we have our table. We can then go back to our facility, and we'll just leave the default name of rate table 1. Go back to our facility, select our source, and then up in the arrival mode property, we're going to change from an arrival time to a time varying arrival rate, and then we will just specify the table that we just created. So now we're saying use rate table 1 to specify the arrivals. And so now when we run, what we're going to expect to see is a increase in customer arrivals here between 11 and 1. And if you look at our rates, we have an arrival rate of 60 per hour during this period, and our server can only handle 40 per hour. So during the initial and final intervals, we can keep up with the demand, but during this middle period, we exceed the demand because we have customers arriving at the rate of 60 per hour, and we can only service 40 per hour. So in our model, when we run our in interactive mode, again we'll see the same plot where we have the instantaneous number of customers in the system. And so we'll just let that run and see what happens around 11 o'clock. We're getting close to our 2-hour period, and so now we should see a jump in the arrivals, which of course we do. And now we're not going to be able to keep up with the customer arrivals for the 2-hour period. And so you can see now about 1 o'clock at time 4 hours right here, our arrival rate should again drop, and we should be able to clear our backlog of orders because we have an arrival rate of 25 and again a service rate of 40. So we have quite a bit of excess capacity in the remaining 2 hours, so we're working our way through our queue. And then we end up stopping right at 6 hours. So now that we've implemented the time varying arrival rate, let's stop the model and let's go to our experiment. And in addition to our standard queuing results that we've always looked at, let's add a response for the maximum number in system. So let's do max NIS, and we can go and let's see, this would be customer population, number in system, maximum instead of average this time. So we'll do the maximum number. And when we run our replications now, we see that we have a fairly large queue. Our utilization hasn't changed, but our queue has resulted in an average time in system quite a bit larger. And so we can easily see this if we compare our 43.1. If we just reset, go back to our model, and then let's just go back, instead of having our time varying arrival rate, let's have our inner arrival time. And so Simio remembers our standard inner arrival time, the one for our normal queuing system. And if we run our same 10 replications, we can see instead of in the 40s, we have a maximum of 18.1 and a maximum time in system of 11 minutes. So we can definitely see when we implement the non-stationary arrival process, the blip here, or the lunch rush that we get in the hot dog stand. So go back to our time varying arrival rate, and then go and rerun our experiment to get that maximum value. So clearly what we'd like to do in this model, or in the real system, if you were actually to run this system, is increase the server availability here during the lunch rush period, or you'd have to endure fairly long lines. And so just to review, the non-stationary arrival process, so this is what this is called, it's a non-stationary arrival process. We divided our runtime into 2-hour intervals and implemented the arrival rates using Simio rate tables. So there's our rate table where we just specified the events per hour, and then we told the source object to use that rate table to specify arrivals.